So today we are going to dive into shaft design, okay? The design of shafts. Now a shaft is actually a rotating machine element which is used to transmit power from one place to another. The power is delivered to the shaft by some tangential force and the resultant torque. So torque is defined as tangential force multiplied by radius, okay? Or twisting moment set up within the shaft permits the power to be transferred to the various machines linked up to the shaft. In order to transfer the power from one shaft to another, the various members such as pulleys, gears, and etc. are mounted on it. Okay, so you have gears, you have pulleys, you have clutch, everything is mounted, they are mounted on the shaft itself, okay? So, and these elements or these devices or these components like pulleys, gears, clutches, and etc., they actually exert a weight on the shaft that causes the shaft to bend actually. Now, these members, along with the forces exerted upon them, causes the shaft to bend. Now, in other words, we may say that a shaft is used for transmission of torque and bending moment. Now, the various members are mounted on the shaft by means of keys or splines. So let us dive into the failure of shaft. So we design shafts we design most of the machine components based on their failures. So we usually look at their failures, okay? So for shaft, actually, there are two different failures. One is torsional failure. The other one is bending failure. So usually we design the shaft based on these 2 points or the combine of bending and torsion. Now, the shaft may be designed on the basis of strength and rigidity and stiffness. So in designing shaft on the basis of strength, the following cases be considered. Okay, first, shaft subjected to twisting moment or torque only. So we will be looking into twisting moment and torque first. Then we'll be looking into bending moment. That means the design of shaft when the shaft is subjected to bending moment only. Okay, and then part C is due to the combine of twisting and bending moments. So we will be looking at part A at first, then we will continue with B and C. Okay, and then D, shaft is subjected to axial loads in addition to combined torsional and bending loads. Now, these are the 4 categories that we will be looking at for the design of shafts. So first, shafts subjected to twisting moment or torque only. So when we look into twisting moment or torque, the first thing is we will think about, okay, the simple torsion equation, or we'll come about simple torsion equation. So in the simple torsion equation, we have 2 relationships. One is the strength relationship and the other one is the stiffness relationship. So based on strength relationship, we have T, which is the torque, J is the polar moment of inertia, tau is the shear stress on the shaft, R is the maximum radius of the shaft. So the cross section of the shaft usually is circular. So first, T is the torque or turning moment, which is in Newton meter or in Newton millimeter. So most of the time we will be looking at, or we'll be using SI units. So J will be the polar moment of inertia, which is in meter 4, or sometimes it can be expressed in terms of millimeter power 4. Tau will be the shearing stress due to twisting moment, which is in Newton per meter square. You have seen these equations before when you do mechanics of materials. Okay, so R would be the radius of the shaft in meter or in millimeter. Then the next would be, in this equation here, you can see, okay, it describes, okay, it shows that, okay, they are equals to constant. The tau, that is the shear stress over radius, is actually equals to constant C. And this constant C, you can consider that, okay, it can be equals to tau max over R max, or equals to tau min over R minimum. So what does that indicate? That means the shear stress relies on the radius. That means the vertical distance, okay, within a circular cross section from the center of the circle to the layer at which shear stress is to be measured. So if, let's say, for example, you increase the radius, the shear stress will increase. So in case of a hollow shaft, so you will have maximum shear stress when we refer to its maximum radius, or you can have minimum shear stress when you refer to its inner radius or minimum radius. So this will be the outer and this will be the inner radius for the case of a hollow shaft. So the next would be the stiffness relationship. So the stiffness relationship, you have T over J, which is the torque and the polar moment of inertia. G, G will be the shear modulus. Theta here will be the angle of twist, and L here will be the length of the shaft. Okay, so that is what I've shown here. So your shear modulus usually is in giganewton per meter square. So usually it's 10 to the power of 9 Newton per meter square. And then L would be the length of the shaft. Okay, so you have seen formulas like that before, okay, when you before this subject, okay, before this course. Usually it is taught in the mechanics of engineering materials. So first thing, shaft subjected to twisting moment only. Okay, so the torsional shear stress, so based on strength, you have shear stress equals to TR over J. Remember, T is the torque or the tangent, or it is equals to tangential force multiplied by radius. Torque itself is tangential force times radius. Okay, R would be the radius, maximum radius, and J would be the polar moment of inertia. Now, since, okay, we are looking at a shaft with circular cross section, so this will be your x-axis, and this will be y, and this will be the z-axis. So if, let's say, for example, when we refer to turning moment, we will be looking at moment of inertia. The moment of inertia, I is the moment of inertia, about the z-axis. That means we assume that the circular cross section will be rotating about the z-axis. So the moment of inertia, the moment of inertia about the z-axis usually is called the polar moment of inertia. Okay, so, and that would be pi d4 over 32, where the d would be the diameter of the shaft. So if, let's say, for example, you are looking at a hollow shaft, that means you have a hole going through a portion of the shaft, we call it as a hollow shaft. Okay, so the hole that is going through the entire shaft. So the polar moment of inertia, or the polar second moment of area, is given by pi d4 minus d4 over 32, where the d here refers to the external diameter, and the lowercase letter d here would be referring to the internal diameter. So remember, the polar moment of inertia is the moment of inertia when we are taking it about the z-axis. The second moment of area about the z-axis. Then we call it as the polar moment of inertia. So that is the two formula which is commonly used in the design of shaft in the case of turning moment. For bending moment is different. So basically what I have here is examples. So I will be going into the examples with you in the next video. Okay, so basically we start up with basic examples. Okay, basic examples, then we go into some examples which is more complicated or tedious or lengthy questions. Okay, so I will see you in the next slide or the next video. MPa or megapascal. Now part A, you are asked to determine the torque transmitted. And then part B, based on the strength relationship, find the diameter of the shaft that is required to transmit the given power and speed. For this question, we neglect bending moment because we are treating that the shaft only subjects to turning moment or torque. So we are going to design, that means we are looking into what is the diameter of the shaft that is required and what is the torque that can be transmitted and what is the minimum or the maximum shaft diameter that can accommodate this much of power and torque. Okay, so when we look into the design of shaft based on torque, the first thing, remember, we will think of the simple torsion equation, but then this question is based on strength. So the strength relationship give you TJ equals to tau R. So remember, T is the torque, J is the polar moment of inertia. Tau here, it will be the shear stress, which is 42 MPa. So you have 42 times 10 to the power of 6. And the radius, which is unknown yet. Okay, so because we have to design the diameter of the shaft. So first thing is, what we have to do is, based on the power and the speed, we will be able to find out the torque. Or we can also simplify the polar moment of inertia based on the design. So it is pi d4 over 32, remember the J, that is the IZZ, is pi d4 over 32. So based on that, we can find first is the torque transmitted. So we know that power transmitted when any objects which is in rotary motion, we use usually 2 pi n over 60 times t. Now divided by 60, remember, because it is per minute, so you are going to convert this to second in order to get watts. And then n would be in revolutions per minute. Okay, so from this we will be able to determine or to find out the torque. Okay, so this usually is equals to T omega, where omega is the angular speed, which is in radians per second. So that is why from revolutions per minute, if you want to convert to radians per second, so that is why you have to multiply by 2 pi and dividing it by 60. So the speed will be 200. So you got a torque of 954.9 Newton meter. That would be the first part of the question. So, and the torque from the equation, the torque we have found, shear stress is given. So we are looking into this diameter of the shaft, for the diameter of the shaft. And then if let's say, for example, we want to find in terms of diameter, make sure you convert radius here into diameter over 2 in terms of diameter, because radius is considered as half diameter. Okay, so the diameter of the shaft based on polar moment of inertia, that is the term here, which is pi d4 over 32. Okay, which is pi d4 over 32. So use this, substitute into the original equation. So you have pi d4 over 32, and this d over 2 is the radius. So when you look into both sides of the equation, so you can cancel off the 4 here with the d here, so that you get a d cube. And then 32 with the here, you got 16. So manipulating, changing t to be the subject, you have pi d cube over 16 times tau max. Now what we need is the diameter. So our diameter has to be the subject. So therefore, d cube would be equals to, from this, yeah, d cube would be equals to 16t over pi time divided by tau max here. From here, from this equation, you got this. So just substitute the torque that we have got just now, 954.9, and the tau max, which is 42 times 10 to the power of 6 into Newton per meter square. So the answer should be 50 millimeter when you solve this equation. When you solve this, find out the diameter. So the cube here, when you bring it over to the right hand side, should be cube root there, please. So the diameter would be 50 millimeter. So this is the first example. It looks simple if you know or if you remember what you have studied in the previous course. Okay, thanks for now, and then see you in the next slide or video. Thank you. Oops. Sorry. So this, because in this slide or in this video here, I have 2 or 3 examples, if I'm not mistaken. Sorry. Okay, so now let us go to the second example. Now, a solid shaft is transmitting 1 megawatt at 240 revolutions per minute. Okay, so mega is times 10 to the power of 6. Determine, first part, the mean torque and the maximum torque transmitted if the maximum torque transmitted exceeds the mean torque by 20%. By 20%. So you have 120%. So based on that, based on the power transmitted formula, which you have 2 pi n over 60 times T mean. So the n is 240. Okay, so power transmitted is 1 megawatt, so which is 1 times 10 to the power of 6. So from this formula, usually the T, the torque that we found would be actually T mean. Okay, so that is the mean resisting torque. So from there onwards, we can find out T mean is 39.79 Newton meter. Now in the question they ask us, they are asking for maximum transmitted, okay, maximum torque transmitted. So the T max, they say, okay, it is 20% greater than the T mean. So T max would be 120 over 100, multiplied by your T mean. Okay, so therefore is equals to 1.2. So from this, you'll be able to find your T max of 47.7 Newton meter. Then after that, only we go for the shaft diameter. So remember, polar moment of inertia. Okay, the same steps which we have done just now previously. So diameter, okay. So that is d cubed 16t max over pi times tau max. So we are going to use t max here. So the answer should be, for this, should be 160 millimeter. Once if you put in your t max and your tau max, which is 60 MPa. So 60 times 10 to the power of 6. So you would be getting the diameter. The answer for the diameter is 160 millimeter. That is the second example. Sorry. Now for the third example, find the diameter of a solid steel shaft to transmit 20 kilowatt at 200 revolutions per minute, where the ultimate shear stress for the steel is taken as 360 MPa with a factor of safety of 8. Okay, so let us go to part A first. So basically here I have a shaft, a solid shaft, okay, stated here solid shaft. So pi d4 over 32. Then when you look at the power and the speed, so the first thing, let us find out the torque. Okay, before that, sorry, the allowable shear stress. So now based on this, they have given us 360 MPa, which is the ultimate shear stress. Usually we don't do design by referring to ultimate shear stress. So in order to use the value of the allowable shear stress, what we have to do is we have to take the ultimate shear stress divided by the factor of safety, which is given here as 8. Okay, so in order to find the allowable shear stress for the design of the shaft, so which is 360, the ultimate shear stress, factor of safety of 8. So you got your allowable shear stress of 45 megapascal. Okay. Then to the torque transmitted based on the power and the speed. So you use 2 pi nt over 60 again to find out the torque, because usually when the power and the speed are given, the most important thing or the first thing you will think of or you thought of will be finding out the torque. So it will be 60p divided by 2 pi n from here. So the power is 20 kilo and the speed is 200 revolutions a minute. Okay, so from here you will be able to find out the torque transmitted. Then the next thing, part B, is to find the diameter. Part A is we are still in part A. To find the diameter of the shaft. So based on the polar moment of inertia, again, same thing, but then this shear stress here would be the allowable shear stress, not the ultimate shear stress. Yeah, you can't design the components or any machine components or any design by referring to the ultimate values. Usually we take the allowable values after dividing the ultimate with its factor of safety. So from here, we will be able to find out the diameter at 0.0476 meter. So that would be equals to 47.6 millimeter. So you round it up so that you get 50 millimeter, always larger than the value that is found. Okay, never to be lower than the value which you have found. Okay, so when you do the rounding up, because if you were to round up to a smaller value, let's say 45 or 40 millimeter, the shaft won't be able to withstand this amount of stress. Okay, this amount of stress that is 45 megapascal. So if you consider a larger diameter when you are rounding up this value here, they would be able to stand up to something which is greater than 45. They will be able to withstand any stress which go above 45 or 45. So part B, now in case of solid shaft, we have a hollow shaft, which you have a polar moment of inertia for hollow shaft. Okay, which this D here, the uppercase letter D here refers to the external diameter, and the lowercase letter d refers to the internal diameter. Okay, so the diameters of hollow shaft. So you have this by taking the D here, the uppercase letter D or the outer diameter as or twice the internal diameter. So to the power of 4, so that is why you have 16. And then d to the power of 4. Okay, so minus d4. So we are trying to simplify this. So you have the polar moment of inertia now is 15d4 over 32. So based on strength relationship, now we substitute this j here. Okay, so we have this, and then you can strike off the d4 and the d, so you get d cubed, and then 32 with 2 here, so you get 16. Okay, so you have this. Now we will be able to find out the diameter of the shaft with the torque and the shear stress. This will be the internal diameter first. Okay, so the internal diameter will be 24.3 millimeters or 0.0243. Okay, so or you can round it up to something that is slightly larger than this, 25 millimeter. So make use of the 25 millimeter times 2. You will be able to find out your external diameter, 50 millimeter. So this will be example 3 or example 4. Now determine the dimensions of a hollow shaft with a diameter ratio of 3 to 4. You've given us a diameter ratio of 3 to 4, which is to transmit 60 kilowatt at 200 revolutions per minute. The maximum shear stress in the shaft is limited to 70 megapascal and the angle of twist to 3.8 degree. Okay, so this question here includes the angle of twist. So means that we have to consider both maybe strength and stiffness relationship. So the twist they have given 3.8 degree in a length of 4 meter. Now for the shaft material, the shear modulus is given as 80 GPa. So note that the two limiting conditions stated in the question, namely the maximum shear stress and the angle of twist, will each lead to different values for the required diameters. So that means when we consider stiffness and strength, it will lead to a different values of diameters. So and then after that, we would have to choose which one is the exact or which one is the safest design for the condition of based on the 3.8 degree and the 70 MPa. Now the larger shaft here they have given, or I have given you a summary, okay, or a hint that which one to be the correct one, okay, which one to be chosen. Now the larger shaft must then be chosen as the one for which neither condition is exceeded. So now when we choose the largest shaft, that means we choose the larger diameter shaft, it will be able to withstand both the condition. If you choose the smaller one, it will either able to withstand this but fail under this condition, or it will fulfill this but fail under this condition. So the best is to choose the larger value of diameter for the design, okay, so that it would be able to withstand both 70 megapascal and without, okay, without anything greater than 3.8 degree. Sorry, my throat. Now, based on the strength relationship first, T over J equals to shear stress over R. So, and also based on the power and the speed. So you will be able to find out the torque of 2860. Okay, once you are familiar with this, okay, and when you look at the question, you saw power and speed, you will know that, okay, automatically you will have to find out the torque. Okay, so that is a torque 2860 Newton meter. So the polar moment of inertia, so that is this, because this is a hollow shaft. And then they have given us a diameter ratio of 3 to 4. And see how I work it out. Okay, so you have J, T, R over tau. So first thing is we know the torque, we know the shear stress, and we change the radius to half diameter. So the J, okay, so you have this, okay, which is equal to this, okay. The J we found here is based on this formula, and also we know that J can also be equal to pi over 32 D4 minus D4, and they have given us the ratio here 3 to 4. That means you can say, okay, so this 3 over 4 means is D over D. So the larger value should be, the larger diameter should be 4. You should refer to larger diameter as 4 and the smaller diameter to be 3. So you can work out the uppercase letter D over the lowercase letter d to be 4 to 3. If you were to write as lowercase letter d to the uppercase letter d, then you should write 3 over 4 like that. Okay, so the larger diameter should be 4 over 3 of the smaller diameter in this case. Yeah, something wrong here. Yeah. So something wrong here. So you have d cubed, okay, is equals to this value. So you can find out the diameter, the external diameter should be 67.3 millimeter. Okay, so if you were to substitute, okay, 4/3 here for the lowercase, for the uppercase letter d, for the external diameter. Okay, so you will be able to find the external diameter is 67.3 millimeter and the internal diameter as 50.5. These are all mathematical problems. Okay, so that is based on strength. Now, then we look into stiffness because they give us two limiting conditions. So that is why we have to refer to both the relationship. One is based on strength, the other is based on stiffness. So based on stiffness relationship, we have this. Okay. So, and that is your J, which is based on the torque, the length, okay, and then the G, the theta is 3.8 times 2 pi over 360 actually, okay, so you are taking 2 pi to 360, and then if you want to convert, consider pi, you can do so, pi to 180. So you will find your J here, 2.156 times 10 to the power of negative 6. It should be in terms of d to the power of 4 here, yeah? Here. It should be in terms of d to the power of 4, yeah. So you get 32.12 times 10 to the power of negative 6. So when you solve this equation, you will be able to find out the external diameter is 75.3 millimeter and the internal diameter to be 56.5 millimeter. So as compared, so under stiffness condition or the stiffness relationship, I think the diameter is larger, right? So under strength, you have this, okay, external and internal. Under stiffness, you have this, okay? So that is the external and the internal. So after comparing both, we got to know that we have to choose the larger value in order to satisfy one, shear stress, and two, the angle of twist of 3.8 degree. So therefore, this should be our design based on 75.3 mm and 56.5 mm. So thus the dimensions required for the shaft to satisfy both conditions are the outer diameter at 75.3, which you can round it up to think around 80 millimeter, and the internal diameter of 56.5 mm. So you can also round this to something around 60 millimeter. Okay. Now we're going to example 5. Now a steel shaft 510 millimeter long and 50 millimeter external diameter. For part of its length, it is bored to a diameter of 25 millimeter and for the rest to 38 millimeter diameter. Find the maximum power transmitted at speed of 210 revolutions per minute if the shear stress is not to exceed 70 megapascal. Okay, so you have only one limiting conditions. Okay, then part B, if the angle of twist in the length of 25 mm bore is equal to that in the length of the 38 mm bore, find the length brought to the later diameter. So you have to find the length, okay, for the later diameters. Okay, so first I have this drawing here. Okay, so you have 25 millimeter and a 38 millimeter. Okay, so for a hollow shaft, the polar moment of inertia is given as pi d4 minus d4 over 32. So now what I need to do is I apply, okay, the principle of superposition, splitting it up into two sections. One is based on the diameter of 38 mm and the other one is based on the diameter of 25 mm, treating this shaft as a varying shaft. Okay, but then instead of force, we are using torque here. Okay, the torque acting at the section here. Okay, remember this part here must be in equilibrium. So since this is pointing towards the left, this must be pointing towards the right, as you have done in your mechanics of engineering materials. So for the first part, okay, let us find the polar moment of inertia based on the diameter of 50 and 25, external of 50 and internal of 25. So we will be able to find the moment of inertia of the first part, that is AB, with a torque T here, which is unknown. Okay, we assume that the torque transmitted to be equal. Okay, so the second part is based on 50 external and 38 internal diameter. So you have the polar moment of inertia of 0.41 times 10 power 6. Okay, for section AB, okay, we take T over J equals to shear stress over R. Okay, for section AB, so is assuming the shear stress is at its maximum when the R is maximum. Okay, so we are taking this to be maximum for this section. So we have 70 times 10 to the power of 6, that is the shear stress, and the maximum radius for this part is 50 millimeter. Okay, multiplied by JAB, that is the polar moment of inertia of section AB. So you will be able to find out the torque of 805 Newton meter for this section. But then remember, the torque transmitted have to be common. So after we find both section, the torque for both the section, okay, you get two different value of torque. So what we need to do is we have to assume, or we have to consider the correct turning moment for the design. So, and then for section BC, we do consider also the maximum shear stress, 70, with the maximum radius, because we have to consider the maximum radius, because both the cases here, the maximum radius is 50 millimeter. So, which is equal to 0.05. So the only thing that is different is the J, the polar moment of inertia. So for TBC, you will be able to find 574. So when you look at it, there are two different torque. But then initially, we'll assume that the torque transmitted for the whole shaft to be common. That means one torque only. Okay, one torque. But here we have two. Okay, so since for the shaft in series, each part of the shaft is subjected to the same torque as mentioned, and also for both sections to transmit a common torque without failure, the minimum torque is chosen for the safety purposes. We are not choosing the larger one. Okay, we are choosing the smaller one, torque, but then dimensions, we usually choose the larger one. For torque, we usually choose smaller one in order for the whole shaft to transmit the same torque with safety. Okay, Otherwise, if we choose the larger one, either one portion of the shaft will fail. So we don't want that. We want both the section of the shaft is safe to transmit the safe torque. Okay, not the larger one. The smaller one will be the best in order to fulfill both conditions, both the section. Okay, so that is why we have chosen 574 Newton meter for the torque. That means as the common torque. Okay, so these questions there is a little bit of twist, so you must be able to understand what the question wants. Okay, so to prove that the torque transmitted is safe, now we are going to prove whether what we have chosen 574 here is safe or not. Okay, so what we're going to do is we are going to put the torque into section AB and the torque into section BC as well, but by taking 574. So if section AB shear stress, when you look at section AB, if I were to consider 574, I have a shear stress of 49.9 MPa, which is less than 70 MPa. So after comparing with the limiting shear stress, we know that, okay, if I use this value, not the larger one, the smaller one, section AB would be safe. Okay. Then we continue with section BC by putting in the torque of 574. Then you check, okay, for the shear stress in section BC is just nice, that is equals to 70. So that means if I choose 574, it's fulfilled or it satisfies both the section without failure. Okay, without failure. But then if let's say I put 805, the larger torque, okay, so what happened is section AB is safe, 70. But section BC might not. You can see when you put into section BC with 805, you get a shear stress of 98.2 MPa, which is much larger than the limiting shear stress. So it will cause failure to the section BC. So that is why we don't consider larger torque, the larger torque. We only consider the smallest torque in this design. Okay. So the power transmitted, which is the safe power transmission, based on the torque of 574. So this would be the answer for the question. For that diagram that I've drawn, in order to transmit power safely, okay, the power must be restricted to something around 12.62, but not more than this value, okay? Any power which is lesser than this value will do. Okay, thank you very much and stay safe. Yeah, sorry, section B. Sorry. Okay, so you have a stiffness relationship. Okay, so what we are going to do now, since TAB, TBC, the torque is common, the shear modulus is common, and the angle of twist is common given in the question. So what we can say is the polar moment of inertia to the length ratio. You have this, okay, AB to AB, BC to BC. So based on this, okay, now actually you can find this by looking at this equation here based on stiffness relationship. The T, G, and theta, they are common. That means TAB or TBC, or this GAB or GBC, or theta AB or BC, they are all the same. So you can equate both the equation by comparing the J to L. Okay, J to L. Okay, so based on this, you have the length ratio. Okay, so we got to know that length AB is 0.71304 of length BC. Yeah, I've forgotten because there is a part B asking us to find out the length. Very sorry about that. Okay, so they have given us the total length of 510. So since we know LAB is this much of LBC, We can substitute into LAB to find out the LBC. So which is 297 millimeter. And then for LAB is 213